is actually a follow-up talk to the EM-based CaJAGWR seminar in 2008. If I just look at the title, you see the difference? You see the difference. So basically, like I was talking about with LIGO. So I just because I want to motivate maybe more people. But apparently this is not necessary, as only LIGO people are here. So maybe I just okay. Oh, sorry. Right. It gets stuck. All right. So what it's kind of update. So sorry. Somehow the computer is very slow. Okay. Yeah. I just want to mention that. So most of people are still like Li Chao is in a bank. Now this guy is gone, and also this one, Kentaro, is not a Caltech, but now in Japan. And Henny is Hager is in company, and Henny go to bank. So and this guy come here. All right. Now, so I just start. First, this is outline my talk. So first, I just give an introduction of the sensitivity of advanced detectors, and I give a simple model for the detector, and then later on I move to the quantum limited measurement. I will introduce standard quantum limit as usual, and then I will go to this macroscopic quantum mechanics. Several topics here. Okay, now, so what's the after this whole bunch of development, now we come to an exciting phase. Basically, now this is enhanced advanced LIGO, and also for other detectors. Basically, you can see here, for these advanced detectors, the quantum noise will become the dominant noise. Hope so. Actually, even not for advanced LIGO, but just not for enhanced advanced LIGO, the so-called LIGO Pro 2.5. Just for advanced LIGO, if you just have really low thermal noise, you're gonna have the quantum noise dominant. Because for this LIGO 2.5, it assumes a larger, heavier test mass. That's why the standard quantum limit become lower. But for the advanced LIGO, you actually the standard quantum limit is higher, so you still have the quantum noise limited sensitivity if you have a little bit smaller coding thermal noise. This is very important. Basically, from the talk you will see, and also this is mentioned in EM-based talk. Basically, you need this kind of sub SQL, this kind of classical thermal noise, like below. Basically, the classical thermal noise goes below the standard quantum limit in order for all this stuff I mentioned to be able to work. Okay, to warm up, I just give you to start with, I just have a simple model for the detector. So this is a LIGO, but it's too complicated for us to study. Let's just first get rid of the loops, get rid of the vacuum pipes. Now we get this naked interferometer. But still, this is very complicated. We can, since you know that we only focus on the differential motion for the arms, so we can get rid of one other arm. Now we have only one arm. Oh, sorry. Oh. Yeah. Oh, sorry. Now, even in this case, it's kind of tricky. Let's just remove this zero here, and then we get this very nice and skinny model. But this is just to start with. Actually, this model is very simple, basically, but it's not trivial. You actually can get all the ideas what I'm going to talk about is based on this model, almost. And you can pretty much understand the physics from this simple model here. Now, let's set up. So this I just draw the space-time diagram. So here the A is the input field, and you have output field here. Goes in and comes out. So you're wondering what is the physical model like in the quantum case for test mass, basically it's just a harmonic oscillator. And how about the optical field? Is again harmonic oscillator, but they're independent in the sense that at different time they're dynamically independent, but they can be statistically correlated if you want. And actually, after they propagate out, because they're all intact with the test mass, so the outgoing field actually do correlate with each other, but they are dynamically independent. Somehow it's very dry here. Yeah. Now, since I'm talking about a quantum mechanics quantum harmonic oscillator, it's like it would be nice just to give you a brief overview of this, go over the concept of quantum harmonic oscillator. So here it's just simple Hamiltonian, and then you have the wave function. This is for the ground state you're familiar with, and this single excited state. Right. So sometimes it's not this is just in the position representation. It's also good to look at the corresponding phase distribution in the phase space. Then this is the Wigner function. Then it's for the ground state, it's simply the two-dimensional Gaussian distribution. And for the single excited state, you have this Wigner function. It's very interesting to have this negative value here. Yeah. All right. So, and also the 0-point uncertainty, and this is just quite kind of familiar to you, but I just want to go over it. And then another interesting case, which I will mention on and on again, which is basically the squeeze state. And this is the Wigner function. So what I draw here is a projection of the Wigner function in this phase space. So for this one, here, this dashed curve shows the for the vacuum state or for the ground state. And this one has a less uncertainty in position. That's why I call it position squeezed. And then this one has a less uncertainty in the momentum. And in general case, you have this momentum and position are correlated. You have this one. Okay. Now let's just go back. Let's go back. To make this simple enough to study, instead of looking at the harmonic oscillator basically in the spatial, like they are independent different location, we rotate by 90 degrees in such a way that they are independent at different time. So these simple things basically get rid of this how to say, uninteresting free propagation. Make it easier. Okay. Now, what's the test mass and light interaction? The interaction is kind of simple because you just have the radiation pressure of the light interact with basically the position of the test mass multiplied by the radiation pressure. In the leading order, what you get here is alpha is a constant, and x is A1 here is the amplitude curvature for the field. And as you can see here, A1 is just like the position for the field. Now, since you have two harmonic oscillator, this is like many harmonic oscillator at different time. But at each time, you have just one harmonic oscillator, which position, these two positions are coupled. Then what is the equation motion is kind of obvious. Basically, you should get the momentum for the optical field, get instantaneous kick. Then basically this corresponds to momentum. You get a shift which is proportional to the position of the harmonic oscillator, right? And then position doesn't change, right? Because they're position coupled, you only get the momentum kick. Now, similarly here, the position of x is simply a Green function multiplied by this external, like the radiation pressure, because here basically the momentum, you get all this kick from these harmonic oscillators at different time. This is kind of obvious, right? Kind of, and also you have a gravitational wave force, but here is like a kind of weird because the reference point should be here, so such that you have the tidal force, but you know what I mean. But then for this simple kind of scheme, you basically have two questions. First question is going to be from this output data, how much do we learn about gravitational wave? Right? Then also the signal noise ratio. This is give you the subject called quantum limited measurement. And you have the second question, which is basically from the output data, what is the quantum state of the test mass? Then let's go to the quantum state preparation. Yeah, you can ask other more interesting questions, but this is pretty much what you get here. And now let's just look at the first one. I just kind of review the old stuff. This is very important. This is a kind of useful for you to understand the second topic of my second subject of my topic of my talk. And here, just try to answer the first question. Okay. Sorry. I found it. Sorry, I just kind of very dry here. Can I have some water? In this simple question, you actually can basically go into the frequency domain. Here, what I show here is basically the output field. You now can think of. Oh, sorry. Thanks. Oh.
Seminar series we provide refreshments, but nothing for the speaker.
Thank you.
Zero.
Okay, right. Now, in this frequency domain, you can think about like harmonic oscillator, which is independent at different frequency, and instead of a different time. Now, what you have here is basically still the same. There's no change in the amplitude curvature. You get a momentum. Basically, for the phase curvature, you have this additional gravitational wave signal here, and then this term comes from the radiation pressure noise. Now, what I draw here is basically the input noise. You can think about that for the amplitude curvature and the phase curvature, they both have their point uncertainty, and this is called input noise. And then when this goes through the interferometer, the test mass makes this two noise are correlated. You have this nice ellipse here. Then the projection of this ellipse gives you the additional signal. At low, because you know that the response of test mass at low frequency is 1 over omega square. So basically means that the low frequency you get a large correlation, at a high frequency you get a small correlation. That's what you see here is basically this noise ellipse from low frequency to high frequency is basically just become less and less correlated. And now you can look at the noise spectrum. Oh, okay. It's simply what you see here. It's basically this input noise, and at low frequency you have the radiation pressure noise. What's going on? And due to the correlation induced by the radiation pressure noise. And then at high frequency, you get less correlated, and it becomes flat. This is short noise. And now, at here, the locus of this minimum point define the standard quantum limit. Okay, yeah. Now, what you can do in order to basically shape noise to change noise curve, you can change the input noise by introduce this input by squeeze your noise. Then this is what you get here. And of course, in this case, simple case, you get short noise reduced, but at the same time, the radiation pressure noise is increased. Right? Okay. If you are smart enough, then you introduce the input filter in such a way that it always has the right rotation angle. Basically, the detector always sends the minimum noise. So you can both reduce a low frequency noise and also the high frequency noise. Okay. Now you also can add output filter. In this case, you know that there's a correlation among this basically the radiation pressure force. Induce correlation between the output amplitude curvature and output phase curvature. And then if you just make the right rotation, right detection, and then you can cancel the noise. And so it's such that you always sense the minimum noise, and you can completely remove the radiation pressure noise. Okay, now you can add more complexity here, and you can add a signal recycling mirror, which is acting at like coherent feedback. You can modify the dynamics of test mass, and then you can get optic spring effect. And also, you can add more complexity here. It depends on where you put the output field cavity. If you before or after you do you can get different response. And then, of course, you can add more mirrors. But for series, you get more fancy schemes. But for experimental, it's just kind of crazy. Okay, so I add up here another new slide here, which I don't have a number because it's kind of speculative. So we have been always focusing on the single detector. But what happens if you have several coherent detector, like the ET scheme? You have several detectors that are coherent operating, and with this kind of things, you can actually cancel some kind of quantum noise. We have been only look at at a very low level, and also another one is basically we have been focusing on basically the noise are stationary. But what happens if we basically change our interferometer adaptively, in time dependent? Right now we only consider very simple time dependent Home-Dynamic detection, which only give you this only start recently, but not very interesting progress yet. Okay, now let's just try to answer the second question. Basically, from the output data, what would be the quantum state of test mass? So this is a conditional problem. Basically, once you get all the measurement data of the output field, what is going to be the wave function or the Wigner function set or equivalently for the quantum state? So in this simple setup here, because what we get is a Gaussian state, then it's completely described by this Wigner function, which is a two-dimensional Gaussian distribution. And this is kind of familiar to everybody. So the center, which is a conditional mean, and you also get the variance covariance matrix. And this one defines the correlation among the position and momentum. And for this ground state, you basically you don't have any correlation. That's why you basically have a circle here. And then for the pure state, which is has a minimum uncertainty, which is only Heisenberg limited. All right. So now, in the classical scenario, whatever you measure, you always reduce uncertainty. In the extremist case, you can completely reduce the uncertainty, and then you can precisely locate the test mass, just a single point in the classical scenario. But in the quantum case, measurement is always associated back action. Depends on really how you look at the thing, you can get a different state. Okay. So in our case here, it's basically if you have a lower power, optical power, then the position has a larger uncertainty, but your momentum has less uncertainty. And if you have higher power, you basically get position squeezed. You have less uncertainty in the position and larger uncertainty in the momentum. Okay, so now, how can you actually? How can you actually get a consistent description for you to basically take into account both the back action at the same time? You also take into account the basically uncertainty reduction in the classical sense, because measurement reduces the uncertainty. And then this is a standard tool here, which is called stochastic Schrodinger equation, which basically describes how the state of test mass evolves under the continuous measurement of the outgoing field. And then the plot I show here, it's the red line. You get a random kind of the mean position. The mean of the position is kind of random, and also the mean momentum is kind of also random. But for the variance, it starts with the, I use the same initial, basically like the vacuum ground state. So position and momentum has the same uncertainty. And you can see that because I assume a very strong measurement, over time, the uncertainty of the position reduce. And while at the same time, because of back action, I cause large diffusion of the momentum. And then I increase the uncertainty in the momentum. While because of interaction, actually I also create a correlation among position and momentum. In the phase space, I basically start with this kind of a like nice circle here, and then because of measurement, you kick it around, start to random walking, and then also the quantum state evolves. You can say that this is like a quantum state collapse, but you just have a dynamic model for it. You can whatever in your mind, but basically this noisy ellipse gonna evolve, and finally at the final time, it become steady. This is very interesting. So basically, here you have some kind of transient, and then at larger time, you can reach some kind of steady state. Even though the position and momentum is kind of the mean position and mean momentum is drifting around, but the uncertainty become just constant, doesn't change anymore. And then for large T, you get this kind of very nice equation here for the basically this is the final uncertainty for the position and a final uncertainty for the momentum, and this is the correlation among position and momentum. And omega q here, which I defined, which is from the previous input operation, is from this alpha, which is proportional to the power. So you see.
So it's omega.
Okay, so it will become clear later. Sorry. Yeah. So this omega q is actually where basically the frequency which the quantum noise touches standard quantum limit. But anyway, so you can. It's very interesting that it's actually no matter what kind of initial state you start with, it's always end up with the same quantum state with same variance. Basically, measurement, because this kind of back action continues to demolish your quantum state. Like finally, the history is always completely forgotten. Just like yeah, for everybody here, because we interact with people so strongly. Like the initial, like whatever we have experienced in the kindergarten doesn't matter anymore, because it's independent of the initial state. Okay, so if you just want to get this steady state value for the uncertainty, or if you just want to know the final state of this test mass, instead of just want to look at the transient behavior, you can have it also can be derived by using Wiener filtering. This is developed by Yan-Bei Chen in early 2000, and then you can get this very nice exact same formula here. And actually, by using Wiener filtering, you actually can get you can also deal with more complicated noise, like the noise has a more complicated spectrum instead of very, very simple noise spectrum in this simple model. And you can look at the reference mode for more details. So this Wiener filtering, basically from the measurement output, you try to estimate the position and also the momentum by applying some kind of filter, this Wiener filter. And then the final uncertainty is basically by minimize over all the filter, then you get the this noisy ellipse here. Yeah. Now, what about in the real world? Like you also have the servo noise comes in, you also have the sensing noise. Many different kind of noise just comes in, and which is cannot describe by just the simple model which I used. And so how actually can we do some kind of quantum experiment with this kind of, in this kind of scenario? Let's just do some kind of intuitive, this is a very, how to say, just give you some kind of intuitive understanding. So basically, if you define some kind of omega f, which will become clear later on what the meaning of this omega f, but basically describe how strong the thermal noise affects your test mass. And then this omega q describe how strong optical field is intact with your test mass. Kind of frequency is a frequency. And omega s is sensing noise, which add up at the output. Then basically here, the tau f, which is the inverse of the frequency, is the time for the thermal noise to become important. And then tau q, which is inverse to the frequency of this omega q here, is time for the quantum effect to enter. And this tau x, because the sensing noise, is actually the time, minimum time, for you to resolve, basically to resolving this quantum information. Then you can think about it, once you get these three numbers, then you can figure out what kind of sum rule or figure like kind of requirement for you to do kind of quantum experiment. Then obvious should go like this way, right? So first of all, you need the times for resolving quantum information must be short enough before the thermal noise become important, and while at the same time your quantum effect must be enter faster than the thermal noise. Then in terms of frequency, you basically have the reversed direction. Okay. Now, if I just this is the spectrum, noise spectrum. Basically, then you can understand what the meaning by omega f and omega q and omega x. Here, omega x is the sensing noise, which is cross the standard quantum limit, and omega q is where the quantum noise touches the standard quantum limit, and then omega f is the frequency where the thermal force touches the standard quantum limit. If you require this kind of condition here, then you can see that you do require classical noise goes below the standard quantum limit in order to do something really quantum. Right? So, yeah, so this is a, right, okay. It's the, after you include the thermal noise, you can ask you can basically derive what the impurity of the quantum state given the thermal noise. And then you found out that this is the impurity which is defined as how far the quantum state deviates from the pure state. If for the pure state, you know that this one is Heisenberg limited, so this one is given by h bar square over 4. This is simply equal to 0 for the pure state. And if you have a large uncertainty, basically less pure state, you're going to get the large, very big kind of circle. Means the state is not pure. And this impurity, if you just increase the omega s over omega f, basically the window size, which the classical noise goes below the standard quantum limit, you can get a pure and a pure state. Oh, we are getting close, not really. For advanced LIGO, omega x over omega f is almost equal to 1 because we are limited by the coding thermal noise. But for LCGT, almost the same order magnitude. But for LIGO 2.5, suppose we're going to have it in, I don't know, the time scale. But suppose we have better codings and fancy beam, we have a the thermal noise is going to touch the frequency which is around 10 Hertz, and the sensing noise, which is the coding thermal noise, going to touch like around 100 Hertz. So you have factor of 10 here, which basically means that you get pretty much very pure state. Like purity very close to almost pure. And for AEI, this 10-meter prototype, they claim that they can have a factor of 50. Which, yeah, I don't know how they, yeah, but, yeah. All right. So,
so they claim they will?
Oh, they have the noise curve.
Right.
They have the noise curve.
So they say they have that now.
They have the design.
The design.
Yeah, design. Okay. So this is all design, right? None of this exists. It will be there. Okay. Then, sorry. Oh, okay, here. So this is another interesting thing we just figured out recently. It's basically, if you only demonstrate it, you can prepare some kind of pure Gaussian quantum state. It's not very interesting because just like a kind of a noise ellipse, which is Heisenberg limited, but it just kind of Brownian motion anyway. But what is interesting, if you can do something, it's really quantum. It's just, you need to show something like quantum entanglement. And we recently figured out that it turns out that the output field is always entangled with test mass, even at room temperature. What does it mean? It basically means that the output field and then test mass have some kind of quantum correlation. This means that whatever we do on what we actually decision or what kind of measurement we perform on the optical field, we have instantaneous influence on the quantum state of the test mass. This is called quantum entanglement. Very weird, but it's there. So basically, after the field interact with this test mass and it goes away, it depends whether you chose to measure like what kind of quadrature you're going to measure the light. You can measure like zeta 1 or zeta 2. If you decide to measure zeta 1, this is what kind of quantum state you're going to get. And however, if you decide to measure zeta 2, this is what kind of quantum state you're going to get. This is a very interesting because if you think about it, once this light and the oscillator, they interact, they almost like fly away. They're not connected anymore. But why you do something here gonna influence the quantum state of test mass there, right? So this is a way of demonstrating that the light and test mass are actually entangled. The experimental consequence is basically, right, you can steer the quantum state of test mass. And then if you just plug in the noise curve, plug in the number of the basically from the noise curve, you almost found that indeed, if you have a large window size, same figure merit, you can get a steerability equal to 1 means you can have almost perfect correlation entanglement. But okay, you can see that you almost, even with a factor of 10, which is a LIGO 2.5, you can steer the quantum state of test mass very nicely. Okay. Yeah. No reaction, so okay. But anyway, so this is an old slide. Basically, you also can entangle the test mass like in the two arms. If you just perform different measurement of the common differential mode. But this is kind of crazy because you have a large, how to say, the laser noise is very high. This is completely impossible. But for this one, which you have a local readout, you can measure the ITM and ETM independently. Then you can create a quantum entanglement among them. And then you can see here the survival time also. Basically, if you have a large sub-SQL noise, you get a better and better, longer and longer survival time. Yes, okay. So this is the last topic. Basically, how can you all this quantum state like quantum entanglement or previous I mentioned is Gaussian Gaussian pure state. They are apart from the entanglement, but for the Gaussian state, it's almost like classical because it's just like kind of Brownian motion, which has uncertainty, which is limited by the Heisenberg uncertainty, but it's still like almost like a classical distribution. You have two-dimensional Gaussian distribution. But how can you beyond that? So we figured out that the usual requirement for the non-Gaussianity is basically require that the lambda over finesse, which is almost a linear dynamic range of your interferometer, need to be comparable to the quantum zero uncertainty. This is very tricky for LIGO or for advanced gravitational detector, because lambda over finesse, lambda is like 1 micron, finesse like 10 to the 1000. This is like 10 to the minus 9. But for the quantum uncertainty of the position, it's like 10 to the minus 19. Like 10 orders magnitude. And so you are really far away from this non-Gaussianity, or basically the nonlinear regime. So how can you do that? How is any solution? And basically, the way out is basically to transfer non-Gaussian state from the light to the test mass, instead of trying to directly get the non-Gaussian quantum state from this kind of nonlinear interaction. Because so here is a kind of scheme here. You just inject a kind of weird quantum state, whatever you like, into the dark port. Then, in this case, you found out that because the coherent amplification of the radiation pressure of the single photons, not single, but for this quantum state, you get the requirement for non-Gaussianity is kind of significantly reduced. This square root n is number of photons enters the bright port over the coherent length of the non-Gaussian state. Even for the 1 millisecond, this guy can be huge because we have a very strong laser. To understand this is actually not difficult, because you can think about it. Even for the reason why we get a coherent amplification is basically come from the fact that the radiation pressure on this test mass is superposed between this dark port and also the bright port. This is also the reason why vacuum fluctuation from the dark port can even drive your test mass and create radiation pressure noise at low frequency. The same kind of, basically you amplify the quantum fluctuation to the macroscopic regime. Yes. So now you actually can, you just do some simple mathematics. It turns out that if you have a small window size, basically the quantum noise is, the classical noise is almost, doesn't have any, doesn't go below the standard quantum limit. You get a positive Wigner function. And if you increase basically make the window size larger and larger, then you start to see the Wigner function become negative. Yeah. For 10, you see the negative Wigner function. This is a complete non-classical, because Wigner function, which is like a probability distribution for your position and momentum, like the become negative cannot be explained by in any classical kind of, don't have any classical explanation. But of course the challenge here is basically you need to really have very long single photon. Basically the single photon need to have a coherence time which is comparable to the dynamic time scale of your test mass, which is like around 100 Hertz or millisecond, tens of milliseconds. So you need really, really long photon. If you multiply the speed of light of 1 millisecond, multiply the speed of light and over 1 millisecond, like a very long photon. How can you generate this kind of long photon? Because in the lab, people only observed photon which is like microsecond. This possible solution is basically you use the automotive squeezer. For the squeezer, if you have a very nice squeezer like in MIT, these people building MIT, and in the very, very low squeezing limit, because you know that a squeezer is kind of produce two correlated photons. If you have very, very low low squeezing factor. You almost just generate 2 photons at each time, 2 photons. Once you can detect 1 photon, then you know that another photon going to come into the detector. This doesn't make a lot of sense maybe to you. Another way is to use the field cavity to shape your single photon. But what do I mean by shape it? So basically, like when the photon comes, you open the port instantaneously, not instantaneously. And then you let the photon comes in, and then you close the port. And then basically the cavity bandwidth determines the length of your single photon. But this requires that you have this instantaneous open the cavity, which is kind of difficult, almost. Okay. And then the final stage, you're going to check, basically, does it really work? Because all this conditional quantum state, you just state in your mind. Just state in your mind because you use your knowledge to predict what's going to be the quantum state like. What do you have is only the center, like the mean position and mean momentum for this quantum state. But the uncertainty or the quantum state itself is kind of inferred. But you don't know whether this is really the case. You can say that you predicted, but nobody's going to believe it, right? So what you can do is basically you pass the information in the preparation stage. You tell the other guy the mean position and mean momentum for the quantum state. You tell the other guy. The other guy, once they get this information, then they're going to measure different quadratures. Because for quantum mechanics, you are not allowed basically to measure position and momentum simultaneously because it doesn't commute. So you're only allowed to measure some kind of linear combination. Then by measure different combinations, and you can figure out the marginal distributions. You can get a different one-dimensional distribution. From that, you can invert back to get a two-dimensional distribution. But for this to happen, you need to prepare the quantum state many copies over a long time, such that you can build up a statistic. And this is in the classic case, this is just you do the CT. Basically, you just do the slicing, and then you build up the three-dimensional kind of what happened in your brain. And in order to do this, you need to measure the quadrature. How can you measure the quadrature? you need to use a time-dependent detection. And here, then basically you need to integrate over the output data. Then you get the signal, which is it can be understood in the following way. Because the position and the momentum, like you measure at different time, then you can invert back to get the some kind of quadrature, arbitrary quadrature you want, by applying different G1 and G2. And then, of course, arbitrary kind of option, kind of choice of G1 and G2 gonna screw you up, but you have to choose them smartly, or smart way. Then basically you need the back action cancellation. It's the same scheme which we mentioned earlier, but in the frequency domain. We cancel the radiation pressure noise. And once you use the optimal G1 and G2, you can figure out the added verification error, the noise, or pixel size. Yeah, right, in the Photoshop. Do you know, I don't know whether you guys use Photoshop or not, but basically you can use a Gaussian filter, which you can choose the pixel size. If you use a large pixel size, then you can blur your image kind of significantly. But if you use a very small pixel size, you only blur your image kind of very little. You almost have no effect on the image at all. So here is the pixel size is actually, in this case, it depends on the ratio between omega f over omega q and the omega q over omega x. Again, if you have a large sub-SQ window, this pixel size becomes very small. Means that you almost recover the quantum state, the true quantum state. And now here, I just show here, it's to demonstrate what's going on. So you have the original quantum state, and then by by measuring different curvature, this can be go on and on to, this is not only restrict to this discrete numbers. And then if you have a small added arrow, you basically get a very nice sharp, this kind of distribution. If you have a large arrow, it's basically like applying a very Gaussian filter. You basically make it broader. And then you can, from this one, you can reconstruct a very nice quantum state. But with this one, you basically screw up. Basically, the quantum state is kind of very distinct from this previous one. All right, so this is pretty my last slide. So what we have learned here is this is for nuggets. Is a gravitational-wave detector is a real giant quantum device. Okay, first of all, we're gonna reach standard quantum limit, and we also we can even go beyond that. And of course, you can also prepare kilogram test mass in a pure quantum Gaussian quantum state. If you have this how to say, this classical noise go below the standard quantum limit. And also you have all sorts of things here. Maybe I just stop here. Thank you very much. Wait. Yeah, because I didn't mention that I folded the you mean this one? This one. Because the output field should go this way, right? I just folded.
Extended in
Yeah.
at a given time, right? That's the field that's directly
Mm-hmm. Oh, but the time delay is very small.
okay. And then what do you mean when you're folding
Because in reality, this guy should go this way, right? Reflect it back. But I just folded for make it look nice. Because light should go in and then reflect it back. Goes in and come out, goes in, come out. But I just make all this outgoing field from this side to the other side. No? Okay. Yeah. That's right. Because in the mirror, you look at it, it's almost like the field is coming out the other way. You just extend it.